Howdy, people. Okay, lab 3. Just cleaning up some stuff from part 2 of the lab that we are not doing, just part 1. So let me kind of label some of these stuff for you. Just obey my own rule. I'm going to show you how to plug everything in. Not too much stuff. It's kind of all set up for you. This is a very kind of in the box, out of the box, ready for you type of lab. So this is where we're going to make all our adjustments. We'll get to that in a little bit. Here's our laser. It is going to go through our beam splitter. It is going to split, bounce off both of these mirrors, come back, and arrive at our detector. This is really just a device which will kind of, there's a small hole in it, hopefully you can see. It'll really just serve as a kind of a viewing screen. That's something that comes up a lot in this lab. This piece of cardboard, or anything, really a piece of white paper would be good as well, just to kind of let that stand there as you're doing the first part of the lab, which is more or less, the first part of the lab is to get the interference pattern to happen. So the alignment, more or less. Let's kind of take you around to some of these other parts. So just to give you a little better view here. Laser, beam splitter, one mirror, another mirror. This is the adjustable mirror that you have some knobs on. Back to the beam splitter, and then the detector. So over here, let's start plugging some things in. This is our Pasco box. Let's plug in our Pasco box. Let's plug in our laser. And then over here is our vacuum pump. So this is our gas cell. This is what we are going to be changing the pressure in. And so the wavelength going through this will change. And that's what the whole theory part of this pre-lab video is about. All right, what the heck is all that equipment for? I struggled to find a way to splice in this theory intro. I was debating just kind of starting with this instead of going there first, but I did a little bit of a poor job with this theory intro, because when I'm talking about the apparatus, I'm not really discussing what we're doing in the lab. I'm just telling you how to collect the data. And then in this document, I'm not really doing much of, there's a little bit, and we'll circle back. You can see this kind of picture down here where we start to actually talk about how the lab relates to all this theory here, but it's a little bit disjointed. So let me try to, now that part of the video has at least given you a little bit of an intro to what the components of the lab are, let me just explain to you the objective of this lab is calculating the refractive index of air. And so that gas cell that I just pointed to in the video is something that we can control the pressure of. So how does controlling the pressure of that gas cell, in that video, I just, kind of gave a hand wavy, we change the pressure and then the wavelengths will change in there. What the heck does all that mean? All right, so let's go through this a little bit slowly. This video's theory intro is quite a bit more substantial than the speed of light, right? The speed of light was just the definition of velocity, basically. This one's a little bit more substantial. So I may find some, I looked through, what I did was I reached out to Professor Benson and found out what textbook y'all used for modern physics. And that actually, that course, starts with quantum mechanics. So this maybe what I'll do is I'll reach out to Professor Schick and find out what your intro textbook was, and then point you to, what section of the textbook that's in. But more or less, I mean, if you just look at the Wikipedia article for the refractive index, almost a lot of the beginnings of that are in there. And then what I've done is this, lab manual is a little bit hard to understand what the heck is going on here. So I think my explanation may help a little bit here. As I mentioned at the very beginning of this video, we're only doing part 1. Okay, so let's just very, very slowly take a step back. What the heck is the refractive index? So this is one that you may recall. This is if we were to think of an equation, if someone were to ask you what the refractive index is and you only had an equation, you couldn't use any English words, maybe you would use something like this. It is the ratio of the speed of light in a vacuum to the speed of light in some medium. So first things first, why are those different, right? What's special about the vacuum? Well, it has no pressure. That's a little bit of a jump. What does no pressure in the vacuum mean? It means that it's empty. And so my apartment right here, this room has pressure in it. And so how could I feel that? There are molecules pressing on all the walls. In the vacuum, there is no pressure because there are no molecules to push on stuff. So how does that have anything to do with this equation, the speed? So it more or less has to do with the word refract. Another word for refract, if you were to, that's kind of a very sciencey word. You could also say bend, right? How much does I, if we look at the index of refraction, that is some climbing stuff. That's not the right tab here. Teaching stuff. Refractive index. So the very first thing that you may think of with refractive index is like Snell's law, right? It's how much bending. But that doesn't really tell us why it bends. The reason why it bends, it's never been, these figures are great for quantitative things like upper level E&M, like deriving Snell's law and the Fresnel equations. But why does this happen? I actually found a kind of a neat little GIF for this, like this. So if there are things in the way, if we think about light as both a particle and a wave, it's going to collide with some stuff. And so it's going to need to kind of ricochet throughout all these molecules in order to get where it needs to go. And so that is why the speed is going to be slower, right? This little wavelet of light takes longer to get from one side of the screen to the other because it has to collide with all these things. And so that's what we're seeing. That's why these things actually bend. So just in terms of relating this to pressure, right? This glass it's a higher pressure environment because there are molecules in there and it will press on the whatever container the glass is in, as opposed to the vacuum, which has no pressure because there are no molecules in there pressing on the outside. So to summarize what we've discussed so far, if a environment has low pressure, well, the vacuum doesn't have any molecules, but let's just say high pressure and low pressure, spaced out molecules. That means there are less collisions. So you can imagine like if this were not glass, but air, right? Air has less molecule. It's a gaseous. Yeah, that's an adjective, gaseous. Fluid substance as opposed to a solid of gas, it will have less molecules, so there'll be less collisions. The light will travel faster through that. So in this context, what we're seeing is low pressure, spaced out molecules, less collisions, lower refractive index. So think about the refractive index as how much it bends. So far, if we were to, think about this in terms of, remember this N symbol, that is what we're saying the refractive index is, N. So far, we've determined that the refractive index is dependent on pressure. Okay, so now let's take a little bit of a step back here, because what we're going to be doing is we are going to, in this lab, in that gas cell, effectively what we're going to be doing is changing the pressure. And what we're going to be observing in the lab is interference. And interference is about wavelengths constructively and destructively interfering. So somehow we're going to need to relate pressure, refractive index, and wavelength. Well, if the things that are traveling are waves, we can think about what is the speed of the wave. And there's an equation for that in terms of the wavelength. So let's look at that. Think about this, the defining speed of a wave. We think about, okay, what is speed? It's distance over time. So distance, that's the wavelength, and over time is frequency, how often the wave oscillates. So now what we can do is we can think about this in terms of not the speed changing, v. If we think about these two things, what's special about the frequency? The frequency is something that is determined by the source, in our case, the laser. So regardless of what medium we're shining the laser through, the laser generated the pulse. And so that has the same frequency. So the frequency is not going to change. So what does that mean? If the velocity has to change, that is not changing. It means the wavelength has to change as well. So if we know that the velocity in some medium, sorry, I kind of squeezed some things in here. If the velocity in some non-vacuum medium or material is another word you can use for that, is less than the speed of light in the vacuum, so c. That's I'm using these little knots just to match up with the lab manual because that's what they were using. The knots are for the quantity in the vacuum. So in other words, we could say C is also V naught, for instance. Um, the frequency in the medium is the same as the frequency in the vacuum because it's coming from the laser, and that is just based on its inception or its generation, not based on where it is currently. That means the wavelength in the medium has to be less than the wavelength in the vacuum. Okay, so what does that mean? That means as this light is traveling through this vacuum cell, the wavelength of the light, right, it's going to be quite small, right? Let's just guess the wavelength of the laser is, let's say 600 nanometers, something like that. There are definitely a bunch of 600 nanometers in I believe our gas cell is around 3 centimeters. So there are a bunch of wavelengths in there. And what we're realizing now is that the wavelength changes when we change the pressure because the vacuum and the medium are different. In our case, the medium is air. So air has a larger pressure than the vacuum. So that means when we change the pressure of that gas cell, more wavelengths will fit inside the gas cell because the speed of the light moves slower when we increase the pressure. That's a lot right there. So just pause, see if that kind of makes sense based on what we've discussed so far, and let's kind of try to move forward with how we're actually going to use that in terms of measuring things in this lab. So bear with me. It's a little bit of a long explanation here. So let's utilize what we just found, this extra definition with the speed of the wave that we're working with. So we're starting with the refractive index equation, the ratio of the speed of light in the vacuum to the speed of light in some medium. And if we're writing the speed of light in terms of the wavelength of the material and the frequency, well, the frequency isn't changing. So we can say that this is changing, the wavelength of the material. And now let's factor something out here, because now what is C over the frequency? This is a speed, meters per second, and this is per second. So bring that up into the numerator, and this is a unit of distance as well. So now we can say that the refractive index is also a ratio of the wavelength of light, or anything, the wavelength of the light in the vacuum to the rate, a ratio of the wavelength of the light in the vacuum to the wavelength in the medium. This is all, quite frankly, this is probably all in the first, well, not quite. Oh yeah, it's literally right there. It's just rearranged a little bit in that equation. So that's what we're working with so far. Okay, so now we have an equation that tells us that the wavelength of the light in the medium is the wavelength in the vacuum divided by the refractive index. Okay, so what we have control over in this lab is the pressure in that gas cell. And what we're going to be doing is how can we quantify how much that wavelength is changing? So that's going to be, I mean, can we measure the difference between 600 nanometers and 599 nanometers? Probably not. But what we may be able to do is count how many wavelengths in the gas cell fit, right? How many wavelengths are in there versus how many are in there when we reduce the pressure to zero. So what we're going to be doing is more or less counting how many of these wavelengths fit inside the cell. So this kind of what I'm looking at here is this gas cell. So this gas cell has a length, and we'll call it D, little lowercase d. Here's my mirror. So my light is, remember, coming from the laser, splitting in the beam splitter. It's going there, coming back. And this mirror over here is really only to create the interference pattern. This is really the main thing that we're going to be measuring. So light comes in, it splits in this beam splitter. Some of it goes here, some of it goes there. So right now we're focusing on this. It goes through once, bounces off the mirror, and goes through again. And then once it hits the beam splitter, it splits again. We're really focusing on what we measure over here, but technically the same amount is coming back towards the laser. We're just not measuring that. So, oops, what we are looking at is an equation like this. If we want to say how many wavelengths fit in that gas cell, well, the number of those wavelengths, we'll call it big capital N, and we'll say this is I, like initial pressure. So for us, the initial pressure is going to be, we're going to be starting our experiment when we're close to vacuum. So our initial pressure is going to be how many wavelengths fit when we're at more or less vacuum. We're not going to be able to get all the way down to the vacuum, but we're going to get pretty close. And the amount of wavelengths that fit in there is going to be twice the distance of that gas cell. So our little lowercase d, I believe it is 3 centimeters. It's here somewhere. Yes, here it is, 3 centimeters. Okay, so now what we're going to be doing is looking at it in terms of, it may be useful if I zoom out a little bit. I've just tried to draw on more, right there. Initially, we're at low pressure, near vacuum. And at the end of the experiment, we're going to turn off the vacuum pump and let the pressure slowly come back to atmospheric pressure or standard pressure. So at the end, once we get back to atmospheric pressure, the pressure will be higher. And so that means the refractive index is higher. And so more wavelengths fit inside there. Okay, so zoom in a little bit more here. Let's give a little bit more of an explanation as to why more fit. So if I rearrange this equation a little bit, I'm going to rearrange it for n, right? We're gonna try to get an exact, kind of quantitative expression for why there are more wavelengths in the gas cell when the pressure has changed. So let's rearrange for this symbol n. So Ni and Nf, we're just going to solve for each of these, divide by the wavelength. And remember, what was this value? We found an equation for that. It looked like this. So the wavelength, if we plug in, if we put a little subscript on this doesn't change, right? That is the wavelength in the vacuum. That is a set number. That's it. It's a set number. So if that gets an index, a subscript, initial, then that would also get a subscript, initial, because the index of refraction changes when we change the pressure. So our equation is going to look something like this. See, we have the wavelength in the denominator, so we're actually going to be multiplying by more or less the reciprocal of this value here. So Ni or Nf over the wavelength in the vacuum. Okay, so if we know now that the index of refraction is proportional to the pressure, now let's look at this equation. That is a constant, that is a constant, that is a constant, but now these n's are not constants. Those are going to change. So this is telling us that the number of wavelengths is proportional to the index of refraction at the given instant, either the initial or final context. So if both of these things are true, that means if little n is proportional to pressure and little n is also proportional to the number of wavelengths that fit in there, then the number of wavelengths that fit in there is proportional to the pressure. So because we're starting at low pressure, pressure initial is less than pressure final, that means the number of wavelengths that will fit in there at the beginning is less than the number of wavelengths that will fit in there at the end. So how are we going to measure this? Effectively, what we're going to be looking at is two different patterns, the interference patterns. And remember, what's interference all about? It's about kind of like, you can think about it like standing waves. These things come back and then it bounces off the mirror, and the troughs, the peaks and troughs, will correspond to when these things constructively or destructively interfere. And what we will see in this video is that in either case, maybe I'll pause this theory intro right here. In either case, when we turn on the vacuum pump or before we turn on the vacuum pump, the interference pattern is there in both cases. So let's see that in action before we continue on with this. So this is going to our vacuum pump. Through this big coil, this is what we're going to turn the lever when we turn this on. And be careful, I tried cleaning it up when you'll notice we're not in 360 at the moment. 360 is getting some renovations done. This mat is to try to catch any of the oil that seeps out of this giant vacuum pump. You'll notice we have this kind of hamper over it so nobody kicks it or anything. It's giant and it's very old and needs oil, and it's kind of gross. So we'll get to that in a little bit. Kind of coming out the side of this hamper here. Okay, so once we turn that on, we will be measuring the pressure through this little valve that comes out just to get a reading on the pressure, and we will be plugging this into our Pasco box. So this is coming over here, got a little label on here. We're gonna put the pressure sensor in channel A, and then we're gonna put our detector, our light detector, on channel B. Go. Go. That will be going into our computer. And then we've got our light sensor over here, which we will put in channel B. Okay, let's fire this up. We'll plug that in a little bit later. And now let's go about our alignment. So this is where I would like to put my viewing screen up just to get a better view, ultimately. And actually turning the lights off is a little bit better at this stage. I'll do that in just a second. All right, let's get this alignment going. I'm gonna turn on my laser. Again, laser safety here. This one isn't as bad as the speed of light one because it really doesn't ricochet off too many places. The way that I'm doing this is my first alignment, I'm going to try to get, you can see the red dot there. I'm basically just gonna try to get everything in the middle, and then we'll work with the adjustment knobs on this adjustable mirror in just a second. So I'm gonna try to get this in the center, just move my lab jack. And I'm also trying to get it in the center of my beam splitter. But you'll notice the beam splitter is kind of hard. So at the moment, what I'm trying to do is get that red light there in the middle of that mirror. And then I'll worry about that one. So first things first, let's get that one all straightened away. You can already see some interference patterns. See these fringes here, right? Maximum, minimum, maximum, minimum. Try to get this in the middle. That's pretty good. And another thing you can do to try to get it in the middle, because it's going back to the beam splitter, right? It's going out through the beam splitter to those two mirrors, and then it's coming back, and then it's going to the detector and back to the laser. So you see, I've got my dot, my red dot, but then I'm seeing the interference pattern here as well because it's being shot to the detector as well as back to my laser. So that's something you can try as well, getting the beam splitter to shoot it back onto itself. So now my red cloud is kind of right on top of my red dot. Okay, that looks pretty good. Now what I'm gonna do is see how I kind of have on my screen, I've got these two somewhat different circles. Now I'm gonna start doing my adjustment knobs over on my movable mirror to try to get those two things to line up. go. It's a little bit higher. Let's move it a little bit to the left and then bring it down. All right, that looks pretty good. That's a little better. Ooh, that's nice. There we go. So as long as we have an interference pattern, it's okay if they don't line up perfectly. We definitely want to see like that, right? That's not good. That is good. So that should be all right. And then what we'll see, before we actually start looking at the capstone software, I'll put a zoom video for that part. Let me show you what happens when we plug in the vacuum. I'll try to zoom in very closely on this. So we're going to plug this in. And it will be very loud. There is no on button. As soon as you plug it in, it just starts running. Nothing has happened yet, but as soon as I bring this valve parallel with this tube, notice what happens to the pattern. Should be all right. All right, I'm moving the valve. The pattern has shifted, right? And now I'm going to put it back to its original position, and I can turn off my vacuum pump. And ever so slowly, you'll see the pattern start to shift. Try to point them out on the screen for you. At the end of that last part of the video, you can see them shift if you play the video at like 2x speed or something like that, but it is very slow, so I think it's easier to just head over to capstone once we're ready for that. So I've turned the lights off to see the pattern a little bit better. All right, so I do highly recommend, because it's on YouTube, you have the ability to speed that video up. Highly recommend, before I turn the lights off and I left the video playing, trying to show it to you in real time, play it at 2x speed because you can see the pattern changing. So what the heck was going on there? What we're seeing there is the same interference pattern. It's aligned, the lasers are aligned, so we're seeing the interference. We're seeing the fringes of that interference pattern move. And a better way to say that is essentially we're seeing this pattern morph into this pattern. Well, actually, we're actually seeing, because of the way that, what just happened in the video, initially it was at atmospheric pressure and I turned the vacuum pump on, and so it went down to close to vacuum. So actually, more so, a better way to say what we're seeing is that this was the initial condition and that was the final condition. So we're seeing it kind of expand outward. But in the lab, what we're going to be doing is our initial condition is after we've turned the pump on, got it to near vacuum, and then we turn it off and allow it to morph into this. And so that's effectively what we're seeing. And what we're going to see is we're effectively going to be counting how many fringes move past the point that we're analyzing in order to get from this pattern to that pattern. So imagine here's the little hole in our, in that little, thing that's kind of making the intensity a little bit more manageable for the light detector. Imagine this hole is right here. What we're seeing is all these fringes kind of move past in order to crunch up into this pattern. So that's what we're seeing. And effectively what we're trying to do is figure out how many fringes move past one particular point in order for this pattern to morph into this pattern. So if we're going to try to quantify that, really what we're doing is the difference between those two things. The number of fringes in the beginning and the number of fringes at the end. So let's subtract one quantity from the other. I'm just going to define that, we've used these subscripts. How about just n? big capital N is going to be the number of fringes at the end minus the number of fringes that we started with. So let's plug in our equation for these and see how this changes. Notice the only thing that's going to change is the Ni and the Nf, right? These things are just constant, so we can pull those outside. So it's going to end up looking like this. And so what we're going to be doing is, remember, what is our objective? I know this is a little bit long, but remember what our initial objective was. What is the index of refraction of air? So if we are starting at vacuum, then that is not what we want. We don't want the initial. We know what that is. It's 1. The index of refraction of the vacuum is 1 because C over C is 1. This is the variable that we're looking for. And so in our experiment, this is the wavelength of the laser. This is 3 centimeters. This is going to be the variable that we measure in order to figure out what the index of refraction of air is. So let's just start plugging some things in instead of like Ni and Nf. Let's actually plug in what these things actually are. So because we're starting off, we're going to say something like this. And the reason that I'm not saying, N naught and N naught up here is because we're not actually getting all the way down to the vacuum. So we have to do some plotting. So how is that going to work? Effectively, what this is going to look like is we are going to have pressure as our independent variable. That's the thing that we are changing when we change the vacuum and allow it to slowly rise up. And the N variable is the dependent variable. How many fringes need to move past in order to get from the initial condition to the final condition? So in our case, this is going to be, at least for this variable, it's quite easy. Like I mentioned before, when the pressure is at vacuum, the index of refraction is going to be 1. So one thing that we can do a little bit extra here is to say that the index of refraction when this is 0 is going to be 1. So let's move that over here. Remember, this is what we're trying to find, the index of refraction at atmospheric pressure, which would be the index of refraction of air. Maybe, may have just been a little bit easier to write this as air, but I was just kind of trying to get this to look identical to the lab manual to try to make it look as similar as possible so that you can consult both. And this number is effectively, right, this is the index of refraction if we were to go all the way down to 0, which the gas pump or the vacuum pump is not going to be able to do. So that means if we take this, which is a function, right, it is the number of fringes depends on how much the pressure is going to change. And so if we put pressure on the x-axis and the number of fringes that we see on the y-axis, then this variable, the number of fringes that we would see going from some final pressure from 0, so atmospheric to 0, is going to be our y-intercept. Because if this is 0, right, imagine, if we have, I don't know if I'm mirrored or not on Zoom, but if P is on the x-axis, then when this is 0, that's going to be our y-intercept, where this intersects with the y-axis. So that's ultimately what we're looking for in this lab. So just to give you some reference, maybe I will I'll pause here for just a moment to get to the part where I'm analyzing this on capstone so that you have a little more context for what this means. And what we're going to do, right, this isn't going to be shown on capstone. This is why this device is so helpful, because I can still see my pattern, right? And what I want to do is I want to make sure I'm not, I don't want to put that dot, the small dot in the middle of this device. See that kind of that dot right there that's kind of siphoning off our stuff. Obviously, our detector is getting overwhelmed right now. And so what we want to do is put this at a location that isn't at that big giant center maximum, but it's kind of like off center, so that the light detector actually sees the fringes moving. And so now you'll see on my light detector, move this over a little bit, you see how that red dot is like to the side of my detector? That is usually the easiest way to align these things. So I've aligned it with my kind of, these knobs to be at the correct height, those two knobs. Now I just need to move it into the correct position. So I'm gonna move it over ever so slightly until I see it inside that tube. Make sure I don't block this. Over and over and over. And that should be good. As straight as possible. Kind of play around with it, put it on the other side of it, in the middle. Let's head over to capstone so we can see this in action instead of staring at a video that is barely moving. Okay, so let me reduce the pressure again. Turning my vacuum pump on. My pattern is shifted. Turn my vacuum pump off. Unplug. And then we're going to head over here. Okay, so hardware setup. We are going to click on A and then scroll down to our pressure sensor. It is pressure sensor absolute. And then we're going to do channel B, and that is just a regular light sensor. Okay, so that's our hardware setup. We're going to drag a graph over here, put pressure as our independent variable, light sensitivity, intensity as our dependent variable. We're going to set the common rate to 50 Hertz and start recording. And then remember the kind of go-to, right, doesn't look like much right there, does it? We're going to click this button so that we can see it all. Oh, I think my gain is not correct. Yes, it looks like it is at 100. Let me try to very carefully do this so it doesn't get out of alignment. There we go. Okay. Let's reset this. And press our scaling button again. And you can do already, before you even, get to the end, you can drag the smoothness up so it looks as smooth a line as possible. And so now what we're gonna see is more or less a sinusoidal pattern. Peaks and troughs. That looks like one of our peaks. And so what we're seeing here is, that if you play the video at 2 times speed, it's the fringes moving. And that's what we're gonna do. We're just gonna sit here and wait. It takes around 200, 300 seconds for it to get back to, notice it's only at 20 kilopascals and needs to get all the way to 100. So this is what we're doing. Notice we can see the pattern still on our screen, a little bit off center, right? Not at that giant maximum. I found that putting the circle at that giant maximum in the middle, the two kind of things, it doesn't get good data. This kind of off center just a little bit, it sees the fringes moving with, not too saturated light intensity. You'll see, basically, if you put it at the center, you'll see just, it will make a sinusoidal pattern, but it will be much harder to analyze. The analysis for this is, honestly, it's easiest to just do it with a Gaussian. So for instance, this isn't a perfect curved line, right? So what I would like to do, let's see if I can do this while it's running. Highlighter region, oh yes I can, look at that. So this is where the kind of error analysis comes into play a little bit here. Actually, let's stop recording so we can do this analysis. What we want is to analyze more or less the same exact location every time so that the curve is accurate. So I'm going to drag this down to something like, let's do that. How about like 12.6? The same spot every single time. Doesn't have to be, necessarily, but basically what we're doing with this Gaussian, oops. Uh-oh. is we are trying to use the Gaussian down here. And how does the Gaussian work? That number, the P0, is the central location. So that is right here, right? That's the peak of our Gaussian, 19.1. If this were, a perfect bell curve with a peak in the middle, right? You can either do, where is that button? The coordinate data tool. You can, put it at the, just above the curve, but, is it that one? That's 9.2. Is it that one? Effectively, you can also just look at this, 15.7. What's the highest? Oh, I'm dragging the wrong thing. 15.6, 15.6, 15.7, 15.6, 15.7. So you can, right there, but there were two 15.7s, right? So I don't necessarily know which one's the middle. So that's why we're using the Gaussian. It's the easiest way to go about that. And that's what we're doing. So this is now my pressure value for whichever of these curves, this is. This would, likely be something like the 17th or something like that. Let me kind of erase this highlighter region so we're not, because remember that we're counting, once this whole pattern forms, we're starting at 0 when it's at atmospheric pressure. So it'll be 0, 1, 2, 3, 4, 5, 6, 7. This is probably like 15, 16, 17, 18. So in my Excel file, let's just say this was my 18th peak. That would be n equals 18, and pressure would be 19.1. So that's how we're going about this. Have fun, y'all. All right, so as y'all saw in that video, there was a little bit, I had to do a little bit more things before I pressed record, right? The gain on the detector wasn't set correctly, and I was showing you how to not align things, like get the capstone set up correctly before I started. So my video looks like it's starting to collect, peaks at around like 19 kilopascals. So that's why I mentioned like that's probably like the 18th one that you saw. So for reference, mine, I started when I actually did this and took good data. I believe the first, I could probably show you. Let's see. Good data. Interferometry, that's documents, that's why. And capstone takes forever. Anyway, as that's kind of loading up, I believe the first pressure, the last pressure, as you'll see, we need to start measuring at 0. So what we're going to do is say that like probably the peak that we see is like the 20th peak or so. So let's just get that out of there. Let's get this away. Do that. So here's my data. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Looks like, well, not quite. I could, if I wanted to, I could fit a Gaussian to this one. I definitely have enough data to fit that one. I could take the highlighter region right there, put a Gaussian on this, and that should give me, yeah, that looks completely adequate. So this one, just to give you some reference, this was like my 20th peak. And so that was at roughly 11 kilopascals. So the intercept is effectively the n that I would have counted if we had gone all the way down to vacuum. So there's not much more, right? There's not much distance because our vacuum pump actually does get us down to quite a low pressure. So just, to give you some reference, it's not going to be an exact number, right? So it would be kind of crazy to assume that it gets exactly to, one peak when we get there. What we're really looking for is it's an actual decimal number. That's why I didn't give you the actual number so that you have to do the lab yourself. But I counted 20 peaks when I collected my data, and my intercept value was around 22 point blah, blah, blah. And then I believe I mentioned that in the video already, but the thing that we're looking for is the projected number of fringes if we had gotten all the way down to vacuum, right? That's the thing that we're looking for is N0. So that means that we're going to need to start at, we're going to start counting at atmosphere. So basically that means we're starting, let me get rid of this thing to show you the whole thing. We start counting from down here. So that would be n equals 1, n equals 2, n equals 3, n equals 4. And so the number of fringes needs to be, a positive number effectively. And I think that should be it. Yep, that's about it. So the last peak that I got, right, that's pretty darn close to atmospheric pressure. That was my n equals 1 was right around there. So that's like around 99. All right. Now you're all set. Have fun. Get the index of refraction of air. It's a very cool lab to be able to get down to vacuum pressures and things like that. Have fun.